Okay. And then just what the Moyal algebra is to generalise, instead of taking the sign, it actually goes to the exponential. And then you find that if you look at the sign bracket, and this was rather interesting, you find that if you go to order h bar, you get the Poisson. So you've got the classical physics. I mean, what you know about deformation algebra, Moyal deformation algebra, you know you've got the classical limit there. When this parameter, when you go to small values of this scaling parameter. But the interesting thing is that there is also an anti-commutator bracket here, and it's known as the Baker bracket. And the Baker bracket is, for you, Morris, it's just the Jordan product.
Yeah, that's...
It's just the Jordan product.
So why, there's a little history, why is the Baker bracket called the Jordan product, and the Jordan product called the Baker bracket?
No, this is
okay, that's
the Jordan
classical.
product.
It's a classical.
Yeah, it's a classical thing. What we physicists call an anti-commutator is actually a Jordan product. Sorry, it's just that when I talk to mathematicians, they ask me what the hell an I think you did, what an anti-commutator was. Maybe I'll take it on your shoulders. I may not have been you, some mathematician.
I'm willing to ask it if you want.
The mathematician asked me, why anti-commutator, and it's the Jordan product. So this is to keep mathematicians happy.
It's similar to covariance in classical.
Is that? Anyway, this is the important. You've got an extra bit of information there. So clearly, this story of folding and unfolding is not complete because there's something else. And we'll see. And let's have a look. I think we can. Oh, yeah, Morris, this is something for you. You know, I've been twittering on about symplectic Clifford algebras. Well, I found from Roll's book, and we can verify the proof if you're not happy with it, right? That the symplectic Clifford algebra is isomorphic to the Moyal algebra. So when I've been twittering about the symplectic Clifford algebra, it's isomorphic to the Moyal algebra. And I'm defining my symplectic. This is the formal definition, which I'm not very happy with, but I think mathematicians they understand what I'm talking about.
Is this the same as the Moyal algebra, or am I missing something?
Oh, no, this is a good question.
I mean, suppose you take a symplectic basis of E. I mean, suppose you take E of dimension 2, you take a P and a Q. Would you get this?
This is a question I would very much like to have some insight or some information on. Because I came to the symplectic Clifford. Oh, it's a long story. But I've been looking for it for a long time and asking theoretical physicists, do you know about the symplectic? Yes. And I've talked to you about it as well. This view is not directed at you, it's a physics college. But it's actually isomorphic to the Moyal algebra. Anyways, still going backwards. And now the interesting thing here is when, and there's a sort of a, I wouldn't say an isomorphism. Whatever you can do in the orthogonal Clifford algebra, you can also do in the symplectic Clifford algebra. So you've got a symplectic Clifford group, which is the covering group, which is the metaplectic group. And it actually comes directly from these kind of considerations. And now it's interesting that this Baker bracket and the Moyal bracket actually have an analogue in the, take the pure quaternions, for example, where the anti-commutator, if you like, is just the scalar product. Factor 2, who cares? The difference, and the commutator is just the cross product. And so when you come to the symplectic Clifford, you've got the Jordan product is the Baker bracket, and when I don't know when I mentioned that, that goes to just the ordinary product in the classical limit. And then you get the commutator here, which goes to the Poisson bracket. So somehow, the reason why I'm worrying about this, as you know, Morris, is why I'm getting these two equations in the quantum case. And it is all background for that. Sorry, it's a private conversation going on here. No, whatever. Oh dear, I'm sorry, I'm so insensitive with this device. Oh, and that, no, we'll go past that. That's just putting it in there. Now then, this was the surprise to me. Bohm is contained within the Moyal algebra. How do we do that? Well, what Moyal does is he goes to the marginals. In other words, he considers a mean P double bar n here as averaging over this joint probability quasi-distribution function over x. Puts in the wave function, writes r equal to the is again, and what he finds is this P double bar is just Bohm's momentum. Okay, so the Bohm momentum coming to it from this picture is this marginal probability average. Which is not surprising because we're talking about averages.
That's like the test.
Okay. Then you go a little bit further. No, I'm going backwards. It might not. Then if you look at the transport equation for the probability, that's the marginal probability when you integrate over it, you find it's just conservation of probability, which is again the second equation in the Bohm outfit.
And how do you get this one? Can you- I don't know, don't forget that I
Oh,
asked.
that's a continuity equation.
It's very simple the way he does. He takes the F equation, you know, the time development of the F XP, and just uses that.
And then integrates.
And integrates and it's just trivial. Well, it's messy integration. I think it's trivial actually. And now then, what's the transport equation for P double prime? Well, and these, by the way, are the equations in his abstract of his paper. You find you get something which looks like that, which translates into something which looks like that, and which finally gives this, that, with the quantum potential. So you directly get it by looking for the transport. That's using the df by dt equation, putting in the variables, integrating them, and what you're left with is one of the equations that Bohm starts with. And of course, what Moyal does is he doesn't bring that out. It's all there, but it's not brought out. And he just uses s equals log this thing, and then Schrödinger equation pops out. So you're, as it were, he's deriving the Schrödinger equation from this.
Can you remind me, so he starts off with the Liouville equation.
Yeah, then he adds in the characteristic function, which I've shown is the idempotent.
So he gets an equation with a characteristic function.
Then he converts it into